Let's make this full screen. All right. Welcome back to Steel Design. Man, we're in lecture 20. It's been an interesting semester. It's like it flies by, but then with the weather, it feels like we only just gotten started. It's interesting. Okay, a little bit of housekeeping. So the attendance grades. I thought I had uploaded the attendance grades from the last lecture, but I don't know what happened. They didn't stick, or I don't know. So the attendance grades are updated, but that has the last two, like last lecture and the one before that on there. So I just wanted to keep you posted on that. Homework 3.1 is graded. The solutions posted. Homework 3.2 is due today, as well as the exam 1 corrections. They were due at 11. And then homework 3.3 is assigned today. And that'll be the first of 2 homeworks on bolted connection design, because we're going to design bearing type connections today, and then on Monday we're going to assess slip critical connections. Really, just so you're aware, bolted connection design for a bearing type connection versus a slip critical connection is really no different. The only difference is instead of looking up the bolt shear capacity, you're looking up the bolt shear and the bolt slip capacity and then taking the one that governs. And bolt slip capacity is really not that difficult to compute. There's just some ideas that you need to be exposed of, so that'll kind of be what we focus on Monday. So getting things kicked off, let's go back and make sure that everybody's up to par with where we're at. So first off, so for a bearing type connection, we have 2 limit states we need to assess, and that's bolt shear and bolt bearing. So bolt shear capacity, hopefully by now you're familiar with table 7-1 on page 7-22. That's one of the first real design aids that we've been using this semester, and it's pretty. Not only is it pretty easy to use, but it's very convenient, because for any bolt material grade, for any thread condition, for any number of shear planes, well, 1 or 2, which is the vast majority of connections, and for any bolt diameter, we can just look up the capacity like that. For bolt bearing, there's a little bit more to bolt bearing, but hopefully between the examples that we've done in class, the video that I posted on Wednesday, hopefully you see that bolt bearing is not hard. It's not difficult. It's maybe a bit laborious, but it's very rote. It's very plug and chug. You compute your hole diameter, and then you get your bolt spacing, your edge distance, compute LCE, LCI, compute the nominal capacity of an edge bolt, nominal capacity of an interior bolt, and then combine that to get the nominal capacity of the whole section, the number of edge bolts and the number of interior bolts, and then multiply by phi. Not hard, just a little bit to it. Before I get into connection design, I want to see if there's any questions about just the bolt shear and the bolt bearing. I don't want to just steamroll through this. I don't think it's hard, but if there's any calculation that is laborious on exam 2, this is the one that's probably the longest. Like if you can do bolt bearing, you're good. Is sort of the point. So are there any questions on bolt bearing? All right, well, we're going to take that as everybody's good to go. If anybody has any questions, though, you know the deal. Just let me know. Now, don't forget layout requirements. Layout requirements are going to show up a bit today in design land. So layout requirements, remember, they have nothing to do with capacity. They have nothing to do with bolt shear or bolt bearing. These layout requirements are to do 2 things, and that is to facilitate construction and fabrication and to prevent corrosion. If that is an excellent question. Mr. Randolph asked about rivets. Are rivets completely phased out for structural design? Are they phased out for design? Yes. We really don't use rivets anymore in large-scale structural applications. First off, rivets are, to put it simply, they're dangerous. You have to heat them up, very hot, and between the heating and the striking and all that, they're dangerous. They're dangerous to install. The other thing about rivets that is worth mentioning is that they are unpredictable. And when I say unpredictable, I'm not saying that they're like a ticking time bomb. I'm saying that they're unpredictable in terms of capacity. When you compute, like if you go down to the lab and test bolted connections and then compare that to the tests that you do for riveted connections, you find you get a lot more scatter with rivets in the data with riveted connections than you do bolted connections. They're just not as predictable. And now that we have high strength structural bolts that can hold up the necessary load, then we didn't have bolts that were of enough quality to be able to resist the loads that we needed them to in large-scale structural applications. So rivets were the way to go. But now that we've got bolts that can handle it, they aren't that necessary. Now, I do say this with one qualifying comment, and that is that while we don't design structures anymore with bolts, that doesn't mean that you as a structural engineer don't need to deal with them, particularly when you're rating. If you're doing load rating of bridges, you go out, there's a bridge, there's the rivet, it's there. You have to deal with it. So Mr. You stole what I was getting ready to say right out of my mouth. So the short answer is no, but the long answer is in AASHTO. No, don't apologize for that. In AASHTO and in load rating specs for various state DOTs and whatnot, you will find info on how to rate for rivets. And usually what they do is they just are very conservative in their estimates of what is the capacity of a rivet. But we don't really use rivets anymore in modern steel construction for those reasons. They're dangerous and they're not very reliable in terms of computing their capacity. That's a really good question, though, Mr. Randolph. Any other questions? All right. So don't forget that we have our bolt spacing and edge distance requirements. And again, they're to facilitate construction and fabrication and to prevent corrosion. And so if bolts get too close together, it becomes difficult to construct. If bolts get too close to the edge, that can cause workmanship issues. So we have some minimums on bolt spacing and edge distance requirements. As for bolts getting too far apart, if they get too far apart, then we can get water in between the plates, and that's not good. Okay, so with that, I think we've got everything we need to talk about bolted connection design. And the thing is, connection design for the types of connections that we're talking about right now are pretty simple. Okay, so what do? We determine the capacity of first off, we determine the factored load. So if we have a member lapped to another member and we're yanking on it in tension, so the first thing we do is we figure out how much load are we having to deal with. So maybe that's 200 kips, factored load 1.2 dead plus 1.6 live. Let's say that's 200 kips. And then we determine the shear capacity of a single bolt. So we look up the bolt that we're using. So if it's an A325 N 3/4 inch diameter bolt and single shear, we look up the capacity. And so whatever that number is, let's say it's 17.9 kips. So we got 200 kips on the connection. Each bolt can hold up 17.9. How many bolts do you need? Just divide. There you go. So we divide and we get, maybe it's, 10, because if you divide 200 into 17.9, it's not going to come out to a nice pretty number like 10. It's going to have some decimal value with it. And so based on that required number of bolts, I say select a pattern accordingly. And I'm going to kind of talk about what I mean about that here in a second. But the long story short is, you're rounding that up to select a pattern of bolts. Once we have that pattern of bolts, we have to actually lay it out, spacing them from each other and how far apart we're putting them from the edge. Now, we typically use the minimum edge distance to lay them out, and we use the either the minimum or the preferred spacing. And I want to explain why we use minimums and not maximums. So the simplest way to look at that is, let's just take, a tension member here and a tension member here. So let's say they're the exact same tension member, and let's say that the tension member let's just keep it simple, 2 bolts, okay? So the tension member up top puts the bolts at their minimum spacing. The tension member on the bottom puts the bolts at the maximum spacing, okay? So why would you not do the lowercase? Well, the reason why you wouldn't do the lowercase is because, you know, that's the tension member. I also need to have something to connect it to. And for the case up top, you know, maybe the plate looks like this. The case on the bottom, that plate, you know, is a lot bigger. So by using maximum layouts, what ends up happening, the reason, you know, if you use a maximum layout, the connecting elements or whatever it's connecting to ends up having to be a lot bigger, and you end up spending more money on steel than you need to. So whenever we design bolted connections, more often than not, unless we're using some repetitive regular process, and I'm going to talk about that here in a second, we tend to go off of minimums. So either the minimum edge distance and either S-min or S-preferred. And to be clear, anytime that we do a problem, either on a homework or an exam, I'll tell you whether or not, you know, you're going to use minimum or use preferred. I'm not going to make you guess. In fact, on your homework assignment, I'm telling you to use S-min. And I just do that so that we all get the same answer. And I'm going to talk here in a second about, you know, some practices that are done in the real world. So that's the process. And so once you've got the load, you've determined the number of bolts, you've spaced them out accordingly, the last thing you have to do is you have to check the bolt bearing capacity, because just because you've laid out the connection doesn't mean it works. And what I mean by that is you pretty much know that it works based off bolt shear, because you've taken the load divided by the shear capacity of a single bolt to get the total number of bolts, and so you just round that up. So you know it's got enough bolt shear capacity, but because you've laid it out, you don't know if it has enough bolt bearing capacity. So you've got to go through and compute the bolt bearing capacity to check to make sure it works. And if it doesn't work, you're going to have to iterate the connection design if necessary. That's if necessary. And I'm going to talk a little bit about some additional items to consider here in a second. Actually, let's go ahead and get into that. So here's some additional items to consider. Let's say that you're on step 5 and you analyze the connection, you check the bolt bearing capacity, and you find that the bolt bearing capacity is not enough. It doesn't have enough capacity to withstand the load. Okay? A few options, and I think that what you do has to be a function of how bad it is. So for instance, if your load is, let's say your load's 200 kips. Let's just keep the numbers simple. So let's say your load's 200 kips. If you compute your bolt bearing capacity and it's like 196, so it's just not enough, you know, the way I would fix that is if I'm using 2-inch bolt spacing, I might just say, let's just go with 2 1/4-inch bolt spacing. Let's just up the bolt spacing a little bit, or up the edge distance just a little bit. And what that'll do is, if you're increasing your bolt spacing and your edge distance, that's going to increase the bolt bearing capacity. Because again, if you go back to the bolt bearing capacity expressions, the bolt bearing capacity expressions are a function of your bolt spacing and your edge distance. And the bigger those values are, the more capacity you have under bolt bearing, because, you know, you're increasing that LC value. So one thing you can do just to, you know, sort of check and see, to iterate that connection, is just to up your spacing a little bit. And I would suggest that you do that if you only need a little bit more capacity. You could also stagger the connection, because if you stagger the connection, some of the edge bolts are going to have a larger LC than some of the others. I think it might make the math a little more challenging, but you can do that. That is an option. I'm not going to ask that you do that in CE 414, but that is one way that you could increase the bolt bearing capacity. Now, the other thing that you can do to iterate the connection if it doesn't work is to increase the number of bolts. So you pick a connection with 12 bolts. The load is 600 kips, and you compute the bolt bearing capacity, and it's like 300 kips. It's way off. You could increase the bolt spacing a bit, but that, you probably need to add a couple bolts just to make that work. The only other thing I would say is if your math is that far off, I always suggest that you check your numbers, because it's possible you just made a math error. So don't discount that. The other item to consider is I would choose a bolt pattern that makes sense. And so what I mean by that is a lot of times you'll lay out your bolts in sort of a grid-like fashion. So, you know, if you compute that you need 12 bolts, you might say, okay, a grid of 3x4, okay? So, because it's you know, a nice compact section, it makes sense. But let's say you did the math and you got like 10.46 bolts. So you can't use 10 bolts. You round that up to 11. Well, if you're laying it out in a grid, like it goes back to like third grade, like 11 is a prime number, right? So you're going to have like 1 by 11, like a row of 11 bolts. Maybe you ought to just do 3x4 and just keep it like a nice pattern of 12. Because it takes that long connection and makes it smaller. Or you could do a grid of 3x4 and just not use one of them. Like that's another option as well. Just, you know, think a little bit when you lay out the bolt pattern. Again, just use something that makes sense. Don't lay out a bolt pattern that's just long because it's a prime number, you know, something like that. Where's my little thing? Hold on. Come on. There we go. Okay. One of the other things that I want to talk about is the real world. One of the things that you find in the real world is a lot of times fabricators lay out their connection in regular spacing. And one of the regular increments that you see a lot in the real world is 3-inch grids. So using a bolt spacing of 3 inches and an edge distance of 3 inches. That tends to be used quite a bit whenever connections are repeated, like over and over and over again. So a very common instance would be the connection that we talked about in lecture on Wednesday. Remember, we talked about that connection over in the engineering over in the older engineering lab, and there's the roof supporting element, and we talked about the connections on the side. Okay, I would bet that those bolts were 3 inches apart. Okay, whenever you have connections that are repeated a lot, and a very common connection is beam to beam connections or beam to column connections, they're using those things all the time in buildings. And so if for those repetitive connections, a lot of times the fabricators will go with 3-inch spacing. 3-inch spacing meets the layout requirements for a wide array of bolt diameters and a wide array of plate thicknesses. And so it's a nice sweet spot value that tends to get used quite a bit. Now, you don't see it used all the time though. For instance, in let's say building design land, you might see 3-inch grids on the beam to beam connections or the beam to column connections, but maybe for your braces, your brace frames, your gusset plates, you know, stuff like that, you'll see maybe a more economized design because they're not as common throughout the building like the ones that are really repetitive. So you kind of do still need to know how to customize your connection. So, like usually whenever I'm trying to rough out an estimate or rough out like some plate sizes, I'll go with 3-inch spacing in my head just because I know that's about what it'll be, and I can tighten it up later if I need. So that's just something to keep in mind, you know, for real world as well. And finally, I do want to talk about this idea of developing the full capacity. We're not going to use this in our example today, but I kind of want to explain. And this actually relates to step 1. In our process. So in our design, what we do is we take the load on the connection and we divide it by the capacity of a single bolt in order to get the number of bolts. Well, what do we mean by the load? Well, up until now, we've been talking about the load as this external force that we're putting on the connection. So here's the connection, we're yanking on this member, and so we quantify that force, and that's what we're designing the member for or the connection for, etc. Sometimes what we do is we don't use an external force, we actually use the capacity. So for example, we have, you know, a tension member. You know, let's say that tension member is a W shape, right? So we're taking that tension member and we're yanking on it, you know, in tension, right? And so what we could do is we could say, I mean, by now, you should be able to compute phi-pn. Now, of course, phi-pn is a function of what the connection looks like, right? And if you're designing the connection, you don't know what it looks like. But you can make some assumptions, right? I mean, you know how to compute the gross section yielding capacity, so 0.9 FYAG, you also know how to compute. So the net section fracture is what, 0.75 FU times the effective net area. Remember, in design, we would assume that the effective net area is about 75% of the gross area. So you could come up with a phi-PN for that member. And the idea is to design the connection for that load. See, the idea is, you know, you design the connection for that load, and then when you look at that tension member, you know that the connection isn't going to fail. You know that the member is, because whatever you've chosen for the connection, that connection's capacity is higher than the capacity of the member. And that's what we mean by develop the full capacity. So instead of using an external load, you actually use the capacity of the member and say, I'm going to design the connection for that. And so that's a practice that you find sometimes in engineering land as well, just to, again, get an idea of what your connection is going to look like. Okay, before we get into design problem land, I want to take a step back and see if anybody has any questions. Anybody have any questions? Or is it just that it's Friday? That's what it is. All right. Okay. So let's do a connection design example. So we're going to design and lay out a bolted connection for this shown. So I've got a plate lapped onto another plate. So it's a 12 by 7/8 inch plate. We're using some pretty heavy duty bolts on this one. We're going to use 3/4 inch diameter bolts. These are group B bolts. So these would be like A490s. We're going to say threads excluded. So these are some pretty beefy bolts here. And we're going to design this connection for the following service loads. We're going to use a dead load of 115 kips and a live load of 160 kips. And so we're going to design and fully lay out this connection. So let me stop this share. Give me a sec. Okay, so let's give me one sec. Okay, so here's the member that we're going to design, here's the connection that we're going to design. So we've got our loads, we've got all of our data that we need for the connection. So let's just get right to it. All right, so first thing that we need to do is we need to factor the load. So step one is compute the factored load. So that would be PU. And for this problem, you know, we know that's going to be 1.2 dead plus 1.6 live, because that's all the members being subjected to. So 1.2 times so what do we got here? $394. All right, do I have a second on that? I'm making sure everybody's awake today. Good deal. Okay. All right. So that's easy. And I should put like a note over here to design, to develop full capacity. You know, you take your PU as the minimum, you know, of like 0.9 FY AG or 0.75 FU, maybe, you know, AE, or, you know, whatever, you know, you could say this is, maybe assume AE 0.75 AG. Just something to think about. It's not that hard, And again, the idea is that if you've designed that connection to withstand that load, you know that the member will fail before the connection does. Okay. All right. So compute the factor load. Now what we need to do is determine phi Rn for a single bolt. So we're going to go to table 7-1. And so let's scroll up a bit so that we all see what we're talking about here. So we're going to go with the 3/4 inch diameter Group B X bolt. So help me out. Which, by the way, is that all the information that we would need? We've got the bolt diameter. We've got the group. We've got whether or not the threads are included or excluded. What would we be missing? Now, the other missing item is also, you can see it right here in the image, but single shear. There you go. It's a single shear situation. So it's Group B, threads excluded, single shear, 3/4 inch diameter bolt. What's the capacity? All right, 27.8 kips per bolt. There you go. All right, so everybody else getting that? So and so maybe I'll put that. Not too bad, right? It's pretty straightforward. Okay. So now what we can do is we can say, all right, sorry, not VP and VR. Excuse me. So 394 kips on the entire connection. Each bolt can hold up 27.8 kips per bolt. So how many bolts is that? I guess I should put, step 3 on that. Is everybody with me on that? So I'm just saying that if the connection can hold up, or the needs to hold up 394 kips, and each bolt can hold up 27.8, how many bolts do we need? Well, but I see what you're doing there, Mr. Ball, but let's actually write the number, and then we'll do that, because I'm making a point. Okay, 14.17 bolts. Okay, and to be clear, Mr. Ball, you're not wrong at all. So Mr. Ball wrote 15, and so we've got 14.7. Okay, so what we need to do is from this choose a pattern that makes sense, and so 14 rounded up to 15. 15's a nice number if we're going to do a grid-like pattern because it's 5 by 3, right? That makes sense. So that's what I meant is look at the number and see, okay, you're going to choose something that makes sense. So use 15 bolts. Okay? All right. Now, what about step 4? Okay, so for step 4, what we need to do is lay out the connection. All right, so typically what we do is we lay out the connection do minimum edge distance first. All right, minimum edge distance. What is the minimum edge distance for this bolt going to be? And more often than that, how do we determine that? Is there a formula? What do we do? Mr. Spirichinsky asked a question. He said, is 14 a weird number? 14's not a weird number, but we can't use 14 because we need more than that. But I guess I do kind of take your point, because if you're doing a grid, it would be 2 by 7, and so yeah. But you could do like a grid of maybe 3 by 5 and maybe take one out. You know, you could do something like that. You could probably make that work. But I take your point. Everybody's kind of quiet. Does everybody remember how to get the edge distance? The minimum edge distance? There we go. It's 1 inch from table J3.4. Is that 132, is it? Yeah, I think it's 132. Yeah. All right, so again, just so everybody's clear, you know, we're going off of, so if you see here on the camera, we're, 16.1-132, and so we're going off of the minimum edge distance table, so 3/4 inch diameter, 1 inch. That's where that's coming from. All right. Now, I'm going to let chat help me out with this. Do you want to use S-Min or you want to use S-Preferred? I don't think I stated that in this problem, so you all get to decide. What do you want me to do, S-Min or S-Preferred? Somebody gets to pick something. All right, we had S-Min. Now, what is S-Min? What's the formula? Well, the other way around. Yeah, 8/3. So 8/3 times 3/4, so the 3's cancel, and that's going to be 2 inches. So an edge distance of 1 and a bolt spacing of 2. So here's how I'm going to do this. So let's test this out. So we're yanking on the connection like this, okay? Now, we were told that the plate is 12 inches wide. So let's see something. If I did, so there's 2 ways I could do this, right? So I could do, I could do 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Or I could do 1, 2, 3, 4. 1, 2, 3, 4, 1, 2, 3, 4. I could do either one. This one over here would lead to a smaller connection plate. It wouldn't be as long. But the bolts might get too close together. Let me ask you this. If we went with this, so we did 1, 2, 3, 4. Can somebody help me out? What would this distance be? And how many of them would there be? Here, that would be the best thing. So there's one here, one here. Let's assume that it's evenly spaced. So that's 5 of them, right? So what's 12 over 5? That's what, 2.4 inches? So that we could do that because 12 divided by 5 is 2.4, and that meets our minimum spacing requirement, right? Our bolts can't be closer than 2 inches apart, so we could do that. So why don't we try that? Let's try it. I don't think there was, there wasn't anything that says you had to use 3 lines of bolts or 4 lines of bolts. So let's do that. And then this dimension here, that dimension is 1 inch. And that dimension is 2 inches. And so this is our trial connection. Okay, I want to take a second and stop and see if anybody has any questions before we get into bolt bearing. Everybody's kind of quiet today, so I want to make sure you all are, this is making sense. All right, I'm going to assume everybody's good on that. Now, I'm saying that this is a trial connection because I don't know whether or not it meets bolt bearing. And if it doesn't meet bolt bearing, I might have to change some things. So we'll see. All right, so let's go to step 5. All right, so evaluate bolt bearing. So in order to do that, we need that. We need that. We need the thickness, which the thickness was given to us as 7/8. We know the bolt diameter, which means that the hole diameter is what? There we go, 13/16. Sit down over here for this. So 13/16. All right. And then what about FU? Okay. Now we were told this was A572 grade 50. So what's FU? Was that correct? I think it was A572 grade 50. Yeah, A572 grade 50. So what's A572 grade 50, the tensile stress for that? There we go, 65 KSI. And that is... Hold on. I'm going to get to Mr. Randolph's question. That's in table 2-5. Okay, Mr. Randolph's asking if there's pitting on a plate, does that affect does our effective thickness change when computing a load rating? Are you talking also about like corrosion out in the field? Right, short answer is yes. Like you would go out, like if you go out and you have section loss, then you can measure the thickness and then use that thickness in your evaluation. So short answer is yes. I mean, you're not going to have that on a fresh connection that you're designing, for fresh construction. But when you're doing load rating, yes, you can go in and change that. And so you can go in and take section loss at various points and either, evaluate it on a section by section basis, or you can, average it out or something like that. But yes. Okay. Other thing I want to make sure that everybody's clear on for our trial connection, what are the number of edge bolts and the number of interior bolts. How many edge bolts do we have? Just to make sure we're clear on that. No. No, it's so remember, whenever you're yanking on a plate, right? So we're yanking on it this way, right? So I don't know if I lost connection there. I heard an echo here. But if we're yanking on it this way, then these are the edge bolts. Did everybody hear me just now, though? All right, Mr. I didn't understand your question, Mr. Bauer. Can you help me out with that? You might need to turn your mic on if needed, because I didn't understand that. Wait, you are absolutely right. Man, this whole time I went with 12 bolts and nobody stopped me. Man, you are absolutely right. All right, hold on. No wonder everybody was quiet. Hold on. Let's go back to our connection now. Maybe we got to change some stuff up. Hold on. Let's change some things up. Okay. So let's evaluate that. All right. So we still got 3 options. So with 15 bolts, we could do 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Thank you, Mr. Bauer. Or it could be 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Now let's look at this one that's kind of tight over here. If this is 12 inches, what is that spacing going to be? What is that going to be? It's 2. So we can do that because that meets minimum bolt spacing requirements. Like if we computed that and it was like 1.8 or something, then we couldn't do that because that would violate bolt spacing limitations. So we can do that. So let's give it a shot. Let's see what happens. All right. No. There's going to be some jumps in the YouTube video. Yeah, don't forget to like, comment, and subscribe. So this is going to be 5, and this is going to be 10. Yeah, Mr. Bauer, you're completely right. Thank you for that. Okay. But everything else is the same. It's the same bolt spacing, the same edge distance, the same thickness. Everything else is the same. So we can go through and kind of chug through our bolt bearing calculations. So let's see if we can do that kind of quickly. So by now, hopefully, I can do this pretty quickly and everybody's kind of good with this. So we can do LCE is LE minus half a hole diameter, which is going to be, let's see what we got here. So, where we have 1 minus 0.5 times 13 over 16. So that's 0.594, right? LCI is S minus H, so 2 minus 13 over 16, which is 1.188. All right, does that make sense so far? All right. So next we do 1.2 LCE TFU, 1.2 LCI TFU, and then 2.4 dB TFU. All right, so let's see if we can chug these out. And while I'm doing this, somebody check my math. I know I need it today. Now, what happened there? Okay, I'm getting 40.52. All right. Or that's not KSI, that's KIPS. 81.05, and then, whoa, Blackboard just went away. Hold on. Am I still here? Did everybody? Did I go away? At my Blackboard screen. Okay, I don't know what happened there. My Blackboard sort of went black there for a second. It just the screen went blank. I don't know what happened. 2.38 kips. Okay, has anybody been going along with me? Or are you getting the same thing I am? Okay, all right. So RNE is the minimum of this and that, which is 40.52 kips. And then RNI is the minimum of that and that. So that is 81.05 kips. And now that Mr. Bauer corrected my ability to count, RN is 5 RNE plus 10 RNI, which is 5 times that plus 10 times that. So 1013.09. And then I'm not doing anything that you couldn't do. I mean, you can do it by observation. That's what we're doing. Yeah, I don't have a problem with that. And so phi RN was 759.8. Is anybody else getting that? So maybe we'll say this is step A, B, C, D, E. And remind me, what was PU? It was like 394. So comparing this and comparing this, step 5 was to evaluate bolt bearing capacity. Does this connection have enough bolt bearing capacity? There you go. So I think that's our answer right there. So what's the answer? It's this. This is the answer. So So we were supposed to design a connection. There's your connection right there. What do you think? Any questions? Now, while you all are chewing on that, I want to pull something up real quick. I'll show you the homework assignment. So here's the homework assignment. I know we're running out of time. And so very similar problem, only you're going through the web of a C-section, not a plate. So you got to look up the plate thickness from, or the web thickness from the manual. But it's the same thing. I told you to use 2 lines of bolts, so it's going to kind of look like that. You just, don't know how many you're going to use. Is there a way to gauge if the connection is overdone? Well, I mean, you could, like it could be made cheaper but still resist the load. You could take your lowest PRN and do PU over PRN to compute the efficiency. But, I mean, think about what we did. We took the connection, we determined the number of bolts was 14.17, and we used 15 bolts. And we used minimum spacings across the board, and it still worked. Like, we got a lot of bolt bearing capacity, but bolt bearing capacity didn't govern. It was bolt shear. And the reason why is just, look at the numbers. You can go back to the capacity per bolt. What was the capacity per bolt? It was like 24.7. Take 24.7, or sorry, what was it? No, it was 27.8. Take 27.8, multiply it by 15. That is the capacity of the connection, and it's probably going to be a lot less than 750. Take the load over that, that's your efficiency. And I don't think you could really do any better given the geometry. Minimum spacings, minimum distances, and the absolute minimum number of bolts, I don't think you could do any better. I mean, that is a reasonable question, though. Very reasonable. That's an engineer's question right there, Any other quick questions? I know we're getting a little bit over. All right. I'm going to go ahead and stop the recording. On Monday, we're going to do slip critical connections. And then on Wednesday, we get into the other world. We talk about welding. That's all I've got, everybody. You all have a wonderful weekend. We will see you all on Monday.